All right, guys. In this question, we are supposed to actually prove that this ABCD is a rhombus. But it's not just to prove from knowing. We are proving this from the information that we are given. So that is the advantage that we're given here. In the quadrilateral given, we are given the diagonals AC. This is the diagonal that we are given. This AC, BD, this bisect at all. Bisect, this is what you're given, they bisect. Remember, to bisect is to divide into two equal parts. We talked about this. If a line bisects another line AB, it means we've got equal distance from this point A to that line, and from that line to the point B. It has got equal distance in between. So, meaning to say, if they bisect at O, we've got equal distance from A to O and from O to C. The same thing from B to O, that's another diagonal. It has been bisected. So it is equal in length from O to D. They'll be equal. It is being bisected. Something that you're told. You do not even know the shape. Remember, you're supposed to prove. So if you have to prove, don't answer as if you know that question. You answer as if you don't even know that question. Like you know the properties, but don't apply those properties because you are yet to prove. You use what you're given. This is what you're given, right? What else are we given? We're given that AC is 4xy. The whole of the line AC, the whole of this diagonal here like this, it's 4xy. But remember, you're told that these diagonals, they bisect each other. And we said from A to O, from O to C, it is going to be equal. So what it simply means is that AO, which is equal to OC, is simply half of this. AC, the whole of AC is the one that you're given as 4xy. So it's going to be 4xy divided by 2. That's half of it, which is going to be 2xy. So here it's going to be 2xy. Here it is going to be 2xy. All right. Let us move on to the same application again. BC is x squared plus y squared. BC, we are given this side, BC, right? This is given as x squared plus y squared. This is what you're given, and we do not even know about this side or this side because we do not know the shape so far. But we are just given that this is x squared plus y squared. Okay, which is fine. BD is given as 2x squared minus 2y squared. If you take note, there's a 2 that is common there, which can be factored out. So it means BD is simply, if I factor out these 2, this will be 2 into x squared minus y squared. If you take this in a closer look. Okay, which is fine even to leave it like that. BD, all right, let me just write it this way. BD is equal to 2x squared minus 2, which is the same. Just leave it like that, or you can factor out 2. Factor out 2 outside is going to be like this. Okay, the factoring out of 2 outside is an advantage now if you are to calculate BO, because we are given from B to D. What about from B to O? And from O to D, because we say they are equal. Remember, they are being bisected. So knowing this, BO, knowing that BO is equal to OD makes us to divide this by 2. So it's going to be 2x squared over 2 minus 2y squared over 2. Divide each and every term by 2. If you factor out the 2 like this, the way that I wrote it before, you just divide everything by 2. But you have to divide each and every term. So this will be x squared minus y squared. Okay. So by doing this, we have calculated the length of BO. By calculating the length of BO, we are calculating the length of OD, which is given as x squared minus y squared. X squared minus y squared. Okay, this is it, guys. This is what this information tells us. what we are given, this is what it tells us only. So, okay. Now that I want to prove that this is a rhombus now. Okay, this is it. What is it that we can take advantage of? Okay, we know the properties of a rhombus, all the properties of a parallelogram are on a rhombus. Okay? And also, the diagonals bisect at right angles. So from the fact that we are told that the diagonals bisect here, we've got something about a rhombus. But if it is a rhombus, it is supposed to be like this. If it is a rhombus, these diagonals, they are supposed to bisect at 90 degrees. For a rhombus, this would be 90 degrees, 90 degrees, 90 degrees, 90 degrees. Okay. So if it is so that this is 90, this is 90, it means this becomes a right angle triangle, like from B to O to C. Considering that concept, it will be like a right angle triangle, B, O, C. So if it is a right angle triangle, therefore it can follow the concept of the Pythagoras theorem, since we are dealing or we are working with sides. We are given sides on a right angled triangle. On a right angled triangle. What is it that you can think of? You can think of the Pythagoras theorem. You see now the linking up of these topics. Another part is linking up with another part. So we can think of the Pythagoras theorem, because like I said, from the properties of a rhombus, this must be 90 degrees, but we are not supposed to indicate that we are supposed to prove that it's 90 degrees. So what we can simply do in this case to prove that this is a rhombus, simply prove that angle B OC is equal to 90 degrees. Since diagonals bisect at 90 degrees. Since diagonals bisect at what? Since diagonals bisect at 90 degrees. All right. So if we can be able to prove that this is 90 degrees, we are done. We have proved that we have proved that it's a rhombus. So how can we prove that it's a 90 degrees? We use now the sides. We are given the sides. So let's think about what a right angle triangle tells us about the sides from Pythagoras theorem. All right, from Pythagoras theorem, we understand that c squared is equal to a squared plus b squared. All right, hypotenuse squared is equal to the sum of the shorter sides being squared, or a squared plus b squared is equal to c squared, whereby c squared represents the hypotenuse. So if we assume that this is a 90 degrees, suppose this is what we want to do, we want to prove, we are supposed to calculate the same BC, this one, as if it's not there. We assume this is not there and calculate it the normal way that our Pythagoras theorem is supposed to do. If this was 90 degrees, our normal Pythagoras theorem was supposed to be BC squared is equal to, we assume this side is not there. We want to calculate it because remember, we want to prove that truly these sides were being created according to Pythagoras theorem. Like for an example, I'm given this is 3, this is 4. Then I calculate this side, I get a 5. So if I calculate this side and get a 5, it tells me that this is a 90 degrees. So this is what you're simply doing. We are simply proving already what we have. So we are simply calculating the BC that we have, but using Pythagoras theorem. By using Pythagoras theorem, it's a definite thing that this is 90 degrees. It cannot happen in any triangle. It only happens on a right angle triangle. So it automatically tells us that that's a 90 degrees. Okay, let's see. A and B, I said these are the shorter sides. So we can use this side and use that. These are the shorter sides. So you're gonna have x squared minus y squared, which is this side, BO, but it's supposed to be squared. A squared plus B squared, which is the other side, the shorter side, which is 2xy squared. So you square everything, all right? So that is going to be BC squared is equal to, we square this. All right, remember from our brackets, x minus y squared is equal to, all right, x minus y squared like this. X minus y squared, remember we said we can expand this by the this part of first term minus twice the product, which is the product of the first and last plus the last squared. So it's going to be x squared, which is the first term, minus 2 terms, first and last. So this is what we have here, but this is to the exponent of 2. So the idea is not going to change, all right? So, or you just expand your normal brackets, okay? So if this was going to give us x squared, which is this x, the first term is x squared already. So it is going to be x squared to the exponent of 2, that is x squared, which is x to the exponent of a 4, all right? Minus 2xy, all right? So you're going to have minus 2xy. But the x and the y that we have here, it's x squared, y squared. So it's going to be minus 2x squared, y squared like that, okay? Then the last is squared, the last is y squared. So it's y squared squared, y to the exponent of 2 squared, which will be 2 times 2, which is y to the exponent of 4. All right, so this is how you could have expanded these two brackets. Guys, just remember your expansion of your binomial. They're talking about the binomial giving us a trinomial at the end. Or you can just have two brackets of a binomial, x squared minus y squared into the bracket of x squared minus y squared. Expand your brackets properly. Okay, remember we talked about this expansion of brackets from our algebra. All right, anyways, then this part, we are supposed to just square everything. This bracket, just square everything, simplify and see. All right, that's 2 to the exponent of 2, which is a 4. X raised to the exponent of 2, and also y is being raised to the exponent of 2. So that will give us x to the exponent of 4. If you have got higher exponents, you use the higher exponents on the first term and on the last term. The middle term carries the least exponent. I mean, the middle term carries the other term, but the bigger exponent should be from the first and last. So this exponent of 4, put it here. The y to the exponent of 4, write it at the end. So in between, you must think of this exponent of 2. So these are like terms, right? Considering that these are like terms, minus 2x squared y squared plus 4 x squared, this one, plus 4x squared, y squared. These are like terms. So we can consider that addition. So minus 2 plus a 4, that's a positive 2. So that is going to be positive 2x squared, y squared plus y to the exponent of 4. Okay. So this is what we have here on BC squared, which is not exactly what we see here, because this is BC squared. So you'll be wondering, how did we get now to this stage? Okay, I want us to get back to that expansion of brackets that we did previously. We said, if we are given x minus y squared, this is what we talked about. This is what we did previously. We expanded x minus y squared, this one, and we said this gives us x squared minus 2xy plus y squared. These are like theorems in algebra that you're supposed to know, just like theorems that we have in Euclidean geometry. In algebra, we also have the same thing. Remember, we talked about this in algebra. Also, if this is x plus y squared, this is what this was for minus, it can be plus y squared. This is just going to be the same as the previous, but only that this part is going to carry a positive. So it's going to be x squared plus 2xy plus y squared. So these are referred to as perfect squares. These are perfect square expressions. If you still remember your perfect square expressions, where we said this is simply the first term being squared. This is your last term, the first term. Then here we've got 2xy, the product of the first and last, 2xy. So if you consider that here it's x to the exponent of 4, it's simply the first term, x, like this, to the exponent of 2, to the exponent of 2. This is what it means. Plus 2x squared, y squared, plus the y to the exponent of 4 is same as y to the exponent of 2 to the exponent of 2. So as we can see, we have that condition, s squared and s squared, s squared and s squared. And the middle term being 2xy, which is 2x, which is the product of the first and the last. So it means this is our first, this is our last. So if that is our first and that is our last, it means this can be factorized as the first plus last squared. The first, which is x squared, the last, which is y squared, everything squared like this. That is how you're supposed to factorize this. Or you can apply your basics of factorization, but we could have factorized that way. Then to find BC, we're just going to introduce the square root. The square root both sides to remove the square. Remember, the square root neutralizes with the square. The square and the square root cancels always whenever you see that. So this is BC is equal to the square root, and the square cancels. So that will be x squared plus y squared. This squared is cancelled with this square root. So we're just left with what is inside of the bracket. And this is the exactly BC that we have before, which is x squared plus y squared. So there is no way this BC was calculated. It was calculated this way. And this way can only, this way of the Pythagoras theorem can only be used if this is a right angle triangle. If this is a right angle triangle. So by default, therefore, it tells us that this angle at O, which is BOC, is 90 degrees. BOC is equal to 90 degrees. All right. So if angle BOC, this one, is equal to 90 degrees, therefore this is a rhombus. There is no way, because there's no you can use Pythagoras theorem on an angle where there's 60 degrees. You can use Pythagoras theorem only if there's a 90 degrees. So that's, we calculated, like we wanted to calculate the hypotenuse along as at BC. And we did that. Remember what I was explaining? And we obtained the same answer, but we calculated as if it's not even there, but we obtained the same answer. From Pythagoras theorem, guys, there is no way, there is no way. That means this must be 90 degrees, because that is where only Pythagoras theorem is used, on a right angled triangle. So if BOC is equal to 90 degrees, therefore, this makes it to be a quadrilateral. All right? That is such that BAB, or you can just have this, therefore, it's what? A, B, C, D. All right, so therefore A, B, C, D. A, B, C, D is a rhombus. All right, so remember the properties of a rhombus that I was explaining, that already we are given that the diagonals here, they do bisect. Already we are told that the diagonals, they do bisect at all. But for a rhombus, they don't just bisect, they do bisect at 90 degrees, right? So diagonals bisecting at 90 degrees, right? Diagonals bisect at what? At 90 degrees. So that makes, this gives us a great, a guarantee to say that this, there is no way this is a parallelogram. It is because of that concept of knowing the properties, like I was explaining, that you need to know the properties in order for you to prove for anything. You must have the properties by the heart. You must know the properties by the heart. And also, as you can see, it's no longer about just the properties, but they want you to get back to your algebra again. Go back to your algebra, revision of those algebraic expressions, simplification, factorization. Do you also recall that? So you're supposed to revise not just one topic, but all topics, because as you can see, algebra is there in Euclidean geometry. We're doing a certain topic, but another topic is now part of the time and is playing a major or a bigger role of that other topic. So please, guys, revise all topics properly. Make sure that you understand each and every topic.